this is a really fun little lesson. The understanding of this isn't going to make or break your being able to do the math that we're going to do for the rest of the term, but I think it's really important to just take a moment and understand the meaning behind the numbers. Okay, so when we're talking about sine, cos, and tan, what is it that we're talking about? Okay, so first of all, it's all about the angle theta. Okay, and we understand that the angle theta represents a angle within the right angle triangle. Okay, this angle right here is the angle theta. Okay, and we know that the angle theta, I mean, it could be as small as 0 degrees. Understand that 0 degrees turns the triangle into just a line, right? There's no angle there, there's no triangle. Okay, but mathematically we can do this. Okay, and then we can extend this all the way up to, well, let's put an intermediate in here. Maybe, I don't know, what is that? Is that 45? It's not quite. Okay, 45 degrees there would mean that that's also 45 degrees. I'm not sure if that's quite true. It's pretty close. Okay, but we can extend this up to 90 degrees. And now, once again, we don't have a triangle. We're just right there. Okay, so as this angle grows from 0 degrees and it grows up until it gets all the way to here. Should I put some more angles in there? There's 10 degrees, and it continues to grow until there it is at about 85 degrees. And finally, we get all the way to the line 90 degrees. So the 0 to 90, this is our range, okay, within our right angle triangle. But when we take the angle theta, whatever angle it might be, and then we say, but what is the sine of the angle theta? Well, now this talks about a relationship, and the sine is the relationship between the opposite side of the triangle and the hypotenuse. Okay, so now let's talk about what happens when we ask about the sine of the angle when the angle changes from 0 degrees up to 90 degrees. Okay, well, let's get away from 0 and 90 maybe. Let's look at 10 degrees and 80 degrees. It's easier to look at. So here's our right angle triangle with an angle theta of 10 degrees. It's very small. Okay, when that's the case, what is the relationship between the opposite and the hypotenuse? So here's the opposite over here, and it's a really short line. Okay, if it was 0 degrees, the line wouldn't even exist. It's so small. It's 0. Okay, very small number compared to the hypotenuse. Okay, now let's move forward to our 80-degree triangle. So now here's our situation. Okay, well, let's go here for a second. So we've got a very small number, almost 0 over something. So 0 over x equals 0, right? So the sine of the angle starts at 0 when the angle is 0. And as the angle grows to something like 10 degrees, we have a fairly small number here compared to this number. The answer of what is the ratio between the two gives you a fairly small number. Okay? Moving on, look at what happens now. Here's opposite, and here's the hypotenuse. Okay, now they're really close to the same. Okay, so if we got all the way to the 90-degree angle, the theoretical, the line, there is no triangle, now it's x over x, and x over x equals 1. So what happens is when we're talking about the sine of the angle, it's going to range from 0 to 1. Okay, 0 meaning the angle is 0, and the sine of the angle equals 1 when the angle is 90 degrees. Okay, our two theoretical triangles, all right, they're just a line, one's horizontal, one's vertical, because the angle has shrunk down to 0 or expanded to 90, which is the same as this angle in here. Okay, so the sine looks at the relationship between the opposite and the hypotenuse, and we get a number that's always going to be a decimal, somewhere between 0 and 1. What about the cos? The cos of the angle theta equals the adjacent over the hypotenuse. So now let's look at these same triangles, but let's look at this. Now we're looking at the adjacent. Now when the angle is very small, the adjacent over the hypotenuse is now this x over x scenario. Those lines are almost the very same length. And we have an answer for the cos, which is starting at 1, but once we have a bit of an angle here, we have a number just slightly less than 1. As we move up to our 90-degree angle, 80 degrees and 90 degrees, okay, now it's this adjacent right here that becomes the very, very small number, and we end up with the 0 over x eventually at 90 degrees. So sine, if we were to graph this, okay, and this is 1 and this is 0, sine begins at 0 and builds to 1. The cos, if we look at the same situation, that's a 1 there and that's a 0, and this is the angle, right? From 0 degrees to 90 degrees. Okay, here, from 0 degrees to 90 degrees, cos begins at 1, right? So the adjacent over the hypotenuse, those lines are the same length when the angle is 0. So it starts here, and at 90 degrees is when it drops down to 0. Okay, always a number between 1 and 0. All right, so that's what the sine and the cos, that's what those functions are doing for us, is they're looking at the relationship between a couple of sides based on the angle and what that angle is. Now tan's kind of messy. Now this is nice and easy, right? Because it's always between 0 and 1. Okay, awesome. Always between 0 and 1. Really easy. What about tan? Well, the tan of the angle theta is equal to the opposite over the adjacent. Opposite over the adjacent. So let's look at what happens when we have a 0-degree angle. Our first triangle here. The opposite is 0, and so that's easy. 0 divided by anything is 0. So if we were to draw this chart, once again at 0 degrees, okay, the answer to the tan of the angle is 0, just like the sine of the angle was 0. Okay, because at 0 degrees, the opposite is 0 and the opposite's on top, so we start at 0. Looks nice and tidy, looks like this is going to work out good. But it gets messy right here. Watch this. Now when we get to this situation, the adjacent is going to get to 0. At 90 degrees, the adjacent is 0. And now we have a number divided by 0. Well, what is a number divided by 0? It's an infinitely large number. Imagine this isn't quite 0. It's a very, very small number when we have an angle of 89 degrees. Okay, we have an adjacent of a very small number. We have whatever this number happens to be divided by a very small number. We have an extremely large number. And divided by 0 is infinitely large. So what happens here as we build towards 90 degrees with our tan function is this goes up off the charts like that. Okay? In terms of practicality, okay, that's where it ends, right? Right angle triangles must have an angle theta somewhere between 0 and 90 degrees. Okay, the wonderful thing about math is that we can move well beyond that. Okay, we've already talked about vectors a little bit back a while ago, so let's just return to that thought for a second. Understand the reason that we're doing all of this is to do math based on an electrical circuit. We've already talked about the fact that we take an electrical circuit, represent the voltage or the current with a vector. So anytime that the vector is in here between 0 degrees and 90 degrees, this all works wonderful. Okay, we can draw an imaginary line down here to 0, which is our reference point, and say, oh look, there's a right angle triangle. Okay, but what if the vector extends beyond 90 degrees? What if the vector is over here? Okay, well, there's two ways to go about this, and this is now getting ahead of myself, but just to finish this thought, we could draw the imaginary line here and say there's our angle theta. We could also go back to our 0 degrees reference point and say, but that's actually our angle right there. Some angle greater than 90 degrees. and we can do the math. We can use sine, cos, and tan to do the math. Okay, I'm going to erase this and I'm going to carry on just a little bit. The way this happens, and this is going to look very familiar, but if we extend beyond the 90 degrees, there's our sine wave right there. Okay, this is 180 degrees, 270, 360. Okay, so we've already talked about the sine wave. Okay, we talked about the waveform when we're talking about an AC power supply or an AC circuit. Okay, we've said it's a sine wave, looks just like that, but that's what this is. This is our sine function. And we just saw what happens when we have an angle between 0 and 90 degrees. Mathematically, we can go beyond that to the full 360 degrees and we can calculate the sine of the angle. The cos of the angle does the same thing. It looks the same, but we started in a different place, right? So this is a phase shift. It's the same waveform, but we started 0 degrees starts at 1 rather than 0 degrees starting at 0. And there's our full waveform. Okay, now tan's the crazy one. Okay, where should I draw this? I'm just going to erase this and start over because tan is awesome. Oh, I want to leave the sine wave for a minute so we can compare back to it for just a second. Okay, so we already saw 90 degrees, 180, 270, 360. We start at 0, we go infinitely large at 90 degrees. I'm going to draw another dotted line here at 270 so I can get this right. Once we get beyond 90 degrees, we start with an infinitely large negative value, which comes back to 180, and then goes infinitely large again at 270. And just beyond 270, we once again start with an infinitely large negative value, and we come back to 360 right there. Okay, just crazy, crazy stuff. But that's what the tan function looks like throughout the full 360 degrees. Knowing that, that's not test material. I'll never test you on that. Okay, you don't maybe have to wrap your head around what that's telling us. But it's really important, I think, to understand the meaning behind the numbers. And when we plunk into our calculator what is the sine of an angle, this is what we're trying to understand, is what is the relationship between two of the sides based on the angle of our triangle. Okay, so that's just a fun little lesson. I wanted to share that with you guys, and then now we're going to move on.